All right, welcome back. I hope you had a great weekend this weekend. I am already in London, so I am missing you all, but you will have a great time this week, and we will be doing some stat review. Don't forget we have a PC on Friday. Thursday will be Throwback Thursday, so don't forget about that. So would you take a minute and do this warm-up, please? What are the probability rules? You might want to look at your formula sheet if you need some hints. Okay, so you should have, so pause it here so you can look. All right, so you should have these formulas. The probability of A union B equals the probability of A plus the probability of B minus any overlap or the intersection of A intersect B. If you think about your Venn diagram, here's A, here's B. If I add these two together, I've counted this piece twice, so I have to subtract off that intersection there. Probability of A intersect B is the probability of A times the probability of B, given that they're independent events. The probability of A given B is the probability of A intersect B over the probability of B. Okay, so going back to your Venn diagram, the probability of A given B is the probability of A, the things that are in A, given that they're in B. So it's these things here. The total probability is everything that's in B. So that's why that one's there. And then remember we have this last one here. The probability of the complement of A, or not A, is 1 minus the probability of A, because remember that all probabilities add to 1. All right, so let's look at a couple examples. All right, so we have an example here where we have people categorized into male, female, smoker, occasional smoker, and non-smoker. We have a total of 768 people that were surveyed, and we want to know the probability that they are a smoker or that they're male. Okay. All right, so if we look at this one here is the probability of A or B. A union B says the probability that's in A or the probability that's in B. So it's all the things that are in A plus all the things that are in B minus the stuff that's in both. So when we're looking at this one, the probability that they are a smoker is 226 out of 768. The probability that they're male is 414 out of 768. This is the probability of A, this is the probability of B, and then we have to subtract off that overlap, that intersection, the probability of A and B. So 127 out of 768, which should be 513 out of 768. Okay. All right, another example. Let's say that the probability that I reach a green light is 30%. What is the probability that I get a green light two days in a row? Now, question is, are those independent events? If I get a green light the first day, does that automatically guarantee I'm going to get a green light the second day, or does it automatically guarantee that I won't get a green light? It has no impact, so it's an independent event. So the probability that I do both is the probability of A times B. So probability I get a green light the first day and the second day. So what's the probability I get a green light the first day? 0.3. What's the probability I get a green light the second day? Also 0.3. What's the probability I get a green light 2 days in a row? It's 0.3 times 0.3, which would be 0.09. What is the probability that I get a red light one day and a green light the other day? Okay. Well, what are my choices here? I can get a red light the first day and a green light the second day. I can get a green light the first day and a red light the second day. I have to add those two probabilities together. What's the probability I get a red light? Well, if the probability I get a green light is 0.3, and the probability I get a red light is 0.7. What's the probability I get a green light? 0.3. Again, they're independent events. Probability I get a green light on the first day is 0.3. Probability I get a red light on the second day, 0.7. And so I add those. 0.21 plus 0.21 would be 0.42. Okay. Next example. Let's say I know that the probability of A is equal to 0.55. The probability of A or B is 0.7. The probability of A and B is 0.2. And we want to know, find the probability of B complement. Okay. Well, we've got a few things here that we can incorporate. We know from our formulas. Actually, talk to your side partner just a minute about this. What do you think? What formula would you use? Well, here's one formula I would use. We know that the probability of A union B, or A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. Well, I know that this is 0.7. I know that this is 0.55. And I know that this is 0.2. So by adding 0.2 to this side and subtracting 0.5 to this side, I get 0.35 is equal to the probability of B. But I want the complement of B, so the probability of B complement is 1 minus 0.35, which is 0.65. If you like to illustrate these on a Venn diagram, you are welcome to do so. You just need to think about what those represent. Okay. Let's try another example. Let's see if I can get a screen in here. Okay. All right, so this example, another one with the probability rules. It says the probability of A is 1/2. The probability of A given B is 1/4. The probability of A or B is 2/3. And we want to find the probability of B. Would you talk to your side partner, please, about this? Pause it here and talk to them a little bit about this. Okay, what did you come up with? What are some formulas you know? Well, we know this. We know the probability of A given B is equal to the probability of A intersect B, or A or B. Oops, excuse me, I wrote the wrong thing there, didn't I? It's the probability of A and B over the probability of B. But I don't have A and B, I have A or B. But I also have this formula that involves the probability of A and B. With the A, this is A and B, this is A or B. So it's the probability of A I got the wrong thing here, don't I? Our formula says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So this piece here. All right, well, let's plug in what we know here. We know that this is 2/3. We know the probability of A is 1/2. We don't know the probability of B. But I have this formula over here that has A and B. And I could solve that for A and B and make a substitution in here. We know that the probability of A given B is 1/4. And I could multiply both sides by the probability of B. And that's the probability of A and B. So this is 1/4 the probability of B. So sometimes we have to incorporate two formulas. So now I have it in terms of the probability of B, and I can simplify. I have 2/3 equals 1/2 plus 3/4 the probability of B. I can subtract 1/2 from both sides. 2/3 minus 1/2, this would be 4/6 minus 3/6, so that would be 1/6 equals 3/4 times the probability of B. So what is the probability of B? That's 4/18, excuse me. Just multiply 4 times 1, 3 times 6, which is 2/9. When you're given a formula, or given parts of two different formulas, see if you can rework them in terms of other formulas. All right, let's look at one last example. It's a tree diagram. Okay. All right, we've got that a bag contains 4 red and 5 blue discs. Okay. 3 discs are chosen without replacement. Okay. Find the probability that we have 2 red and 1 blue. Okay. So let's think about what is our first option. Well, we can have a red disc or a blue disc. What is the probability that we get a red one the first time? We have a 4 out of 9 probability. What is the probability we get a blue one? We have a 5 out of 9. All right, so then we're going to draw another one. That's a 9, by the way. And we can still get a red or a blue. Here we can get a red or a blue. Well, if we've drawn one red out, what is our probability? It should be 3 out of 8. If we drew a red one out and now we're getting a blue one, we still have all 5 blues in there, but we only have 8 marbles. If we drew a blue one out and we now draw a red one, we have 4 out of 8. If we draw a blue one and then another blue one, that's also 4 out of 8. I would like you to think about completing the tree diagram with the probabilities for the last draw. Pause it so you can do that. Oops, that should be a blue. Okay, so pause this and fill in these probabilities. Okay, does your tree diagram look like this? These are the possible outcomes. I can get 3 reds, I can get 2 reds and a blue, a red, blue, red, red, blue, 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 red, red, blue, red, blue, 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 red, and blue, blue, blue. I know that was quick, but you can see what you can get there. We want to know what's the probability that I get 2 reds and 1 blue. So which ones of these things are what I want? Well, that one has 2 reds and a blue. That one has 2 reds and a blue. And that one has 2 reds and a blue. So I'm going to add those probabilities together. How am I going to find those? I'm going to multiply along that tree. So I'm going to take 4/9 times 3/8 times 5. That is a 7. It's kind of hard to see that that's a 7. But 4/9 times 3/8 times 5/9, that is a 9 there, because you haven't drawn any blues, so you still have 5 out of the, and that should be a 7, yes. Okay, so 987 is my denominator. When I multiply that, I get 60 out of 504. Here, same thing, 4/9 times 5/8 times 3/7, 60 out of 504. Here, same thing, 5/9 times 4/8 times 3/7, 60 out of 504. What am I going to do with those 3 probabilities? I'm going to add all of them together. When I add all of them together and simplify, I get 180 out of 504. And when I simplify, I get 5/14. All right, so for tomorrow, actually tomorrow what you're going to have is you're going to have a work day for tomorrow. Tomorrow's work day, you're going to work on page 372 and 373, problems 3 through 8, 18 and 19, and then on page 378 to 380, problems 1, 4, 7, 11 through 19, the odds, and 22.